Hello, and welcome back to the final IB Math speedrun of Chapter 11, and actually it's the final chapter already, so we're nearly done with the book. Not yet done, though. And so we're going to be going through the chapter review of Chapter 11, so let's jump right in. So I'll be doing the even questions, and so the first question is, a digit is chosen at random. Find the probability that it is divisible by 3 or 7. Okay, so we have 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Of these 9 digits, 3, 6, 9, and I think we're counting 0 is divisible by 7, and also 7 is divisible by 7. So from this, we get there are 1, 2, 3, 4, 5 out of the 9 digits that are divisible by 3 over 7, so the probability should be 1/2. I'm just not sure if we're counting 0. I'm pretty sure we count 0. Yeah, so they're not counting 0. So 0 does not count. Never mind, so this is actually 4 over 10 or 2/5. So yeah, that's cool. Okay, on to the next one. And the next question is 10 counters. 10 counters are in a bag. 7 are red and 3 are white. 2 counters are taken out one at a time without replacement. Find the probability that the first taken is red, the second is red, so the next one is exactly, 1 is red, and finally at least 1 is red. So we can draw a tree diagram to help us out here. So let's since they're all red, let's consider the probability that the counter is red or not. So red, not red, then red, not red, or red, not red. And remember, there's no replacement, so 7 are red, so this would be 7 over 10 and 3 over 10. So the probability that the next one is red is 6 over 9. This one is 3 over 9. This one here is 7 over 9. And this one is 2 over 9. So let's just calculate probability. Probability that both are red is 42 over 90. Probability that first one is red, second one is not, is 21 over 90. Probability that this is 21 over 90 as well. And the probability that both of them are not red is 6 over 90. Okay, so the first take is red, 7 over 10. The second one is red. So the second one is red. There are 2 possibilities. We have to add these 2 up. So it's 42 plus 21 over 90, which is equal to 63 over 90, which is equal to 7 over 10 as well. Exactly 1 is red, so we have 2 possibilities, this or this, so it's just 21 plus 21 or 42 over 90, which is equal to 42 over 90, and that is 7 over 15. And at least 1 is red. We can just subtract the case of not being red from 1, so we get 84 over 90. And 84 over 90 is 84 divided by 6, 14, 90 divided by 6, 15 is 14 over 15. Nice. So yeah, that should all be correct. 7, 7, 7, 14. Yep, okay, that's good. Okay, next question. We have a game consists of taking 8 counters which are blue on one side and green on the other. The counters are thrown in the air and land randomly on the ground. If the number of counters which show green is an odd number, the thrower wins. If all counters are the same color, it counts as 2 wins. All other scenarios count as a loss. Find the expected number of wins and losses. Okay. So 8 counters, 2 to the power of 8, 256. So So if they are thrown in the air and land randomly, then there's a 1/2 chance that the person will win. So the win. 2 wins is equal to, actually there's not 1/2 chance. There is a 127 over 256 chance. Since if all 8 are green, then that counts as 2 wins. That counts as 2 wins. So we have 1 over 128 over here. Or this is actually 2 over 256. So if they either throw all green or all blue, it's 2 wins. And then otherwise, so that's 127 over 256. We count that as a loss. So the expected number of, I guess, net wins and losses is, we add up 2 times this, plus 127 over 256, minus 127 over 256. Is it just 4? It's 3? Okay. Oh, but this is if it's an odd number. So what's the probability of it throwing an odd number of greens? 1, 3, 5, 7. So that means you throw 1, 3, 5, or 7 versus 0, 2, 4, 6, 8. So this is equal to, let's calculate the losses first, because this is just easier. This is 2, 4, and 6 if they're thrown. So this is 8 choose 2 plus 8 choose 4 plus 8 choose 6. So this is equal to 8 choose 2 plus 8 choose 4 plus 8 choose 6 is equal to 126. And so therefore there should be 128 wins. So we expect 2 wins from here, 128 minus 126. So this should be equal to actually 6 over 256, which is equal to 3 over 128. So that's the expected amount of wins. I don't know why it says 3 over 256. That's a bit odd. I think it should be 3 over 128. Okay, cool. Next, an energy saving light bulb has a life of H hours, where H is normally distributed with a mean of 1,300 hours and a standard deviation of 125 hours. So first, find the probability that a randomly selected light bulb will last for more than 1,500 hours. Next, the manufacturer offers to replace for free any light bulb which burns for less than 1,050 hours. Find the percentage of light bulbs that need to be replaced. And then finally, if 2 light bulbs are installed at the same time, find the probability that both will burn for less than 1,400 hours but more than 1,200. Okay, Standard deviation, okay. Randomly selected light bulb will last for more than 1,500 hours. You're asking for the probability that the standard normal distribution function is greater than 1,500 minus 1,300 over 125, which is 200 over 125, 200 over 125 is equal to 1.6. So that probability will be equal to, find it on your calculator or here, 0.94, 1 minus 0.9452. So that's going to be probabilities around 0.0548. So that's around like 5%. Yeah. Next, less than 1050. So all the information is irrelevant. It's more or less just z is less than 1050 minus 1,300 over 125, which is equal to z is less than 1050 minus 1,300 divided by 125. It's less than -2. So that would be equal to, or is 2, 1 minus 0.9772. So that's around 0.0228%, which is around 2.28% of light bulbs will need to be replaced. Finally, so both will burn. So we need to find the probability that a light bulb will burn for less than 1,400 hours but more than 1,200. So we have 1,400 minus 1,300 over 125 minus the probability of z burning longer than 1,200 minus 1,300 over 125. So we have, oh, we can just mirror this. This is just, okay. So this probability will just be equal to 1 minus 2 times the probability that it burns for longer than this, because it's a mirrored function. So that's 1 minus 2 times the probability of 100 divided by 125, 0.8. So that's 0.7881. Minus 1, 1 minus 0.7881. So 1 minus 2 times 0.2119. So that's equal to 1 minus 2 times answer, 0.5762. And so since we need to get the probability that both light bulbs will burn for that long, we have to multiply this by, we have to square this. Is equal to, oh, that's wrong, divided, no, cube root answer squared, which is equal to 0.332. So that's around, yeah, 33.2% chance that both will be between those 2 hours. Okay, nice. And the next one we have in a factory. Chocolate bars are produced on one of 4 conveyor belts, A, B, C, or D. A small percentage of bars are not produced correctly for sale. So first, find the probability that a bar chosen at random from the whole output is faulty, and find the probability that a faulty bar comes from conveyor belt D. So it's a, what's it called? This is a axiom. This is bezel. No, not, it's not bezel's correction. What am I doing? Which one is this? This is the, oh, where'd it go? No. This is the union formula. Where is it? It is, I just can't remember the name. I'm looking for the name. It is the, oh here, Bayes' theorem. So anyways, I have to also draw a table, which I have not drawn, because otherwise, of course, this problem would be impossible. So we have the conveyor belt A, B, C, or D. And we have the percentage of faulty chocolate bars, which is 1%, 3%, 2.5%, and 2%. And we have percentage of the total outcome is 35, 20, 24, and 21. So find a probability that the bar chosen from random from the whole output is faulty. So what we need to do is we need to multiply the faulty probability by the percentage probability. So we have the probability that it's faulty is equal to the probability that it's faulty from A, given that A occurred, times the probability that A occurred plus dot dot dot, all of the others. So that's equal to 0.01 0.01 times 0.35 plus 0.03 times 0.2 plus 0.025 times 0.24 excuse me, plus 0.02 times 0.21. So in all, that's equal to 0.01 times 0.35 plus 0.03 times 0.2 plus 0.025 times 0.24 plus 0.02 times 0.21. So I got the probability is 0.0197. So next, find the probability that if a faulty bar comes from conveyor belt, conveyor belt D. And so this is simply equal to this over that, because we have from a Bayes theorem that the probability that it came from D and it was a faulty bar is equal to the probability that it was a faulty bar came from D times the probability of D all over the total probability of a faulty bar, more or less. And so this is equal to 0.02 times 0.21 divided by 0.0197. So this is equal to around 0.213. I believe, yes, that is correct. Very nice. Okay, next we move on to the exam style questions. So we have two events, A and B are independent. It is given that the probability of A is equal to 0.3 and the probability of B is equal to 0.8. State with a reason whether events A and B are mutually exclusive. No, they are not, because the total probability has to add up to 1, and 0.3 plus 0.8 is greater than 1. So therefore, the events cannot be mutually exclusive. Okay, so next, find the probability of, so first, sorry about that, find the probability of A intersection B, A union B. Next, A, given that B did not occur, and finally, A did not occur, intersection B. Sorry, I'm back. So now we'll be covering this question. So next, the intersection between A and B. Well, we assume that, let's see, P of A is 0.3, P of B is 0.8. And we're gonna, so I guess we have to assume that either A or B, oh no, we don't have to assume that A or B always occur. Yeah, sorry, so are these events mutually exclusive? No, because their intersection cannot equal to 0, of course, so 0.3 times 0.8 is not equal to 0, so these events cannot be mutually exclusive. And so for A intersection of B, this is equal to the probability of A times the probability of B, which is equal to 0.3 times 0.8. which is equal to 0.24. So that's intersection. Now A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. This is equal to 1.1 minus 0.24, which is equal to 0.86. Yeah, 0.86. Next, A given that B did not occur. So A given that B did not occur is equal to A intersection B did not occur over the probability that B did not occur. So A intersection B did not occur is equal to the probability of A minus the probability of A intersection B over the probability that B did not occur. So this is equal to probability of A was it 0.3? I don't remember. 0.3 minus 0.24 divided by 0.2. So this is equal to 0.06 divided by 0.2, which is equal to 0.3. So that's the probability. And finally, A prime intersection B. The probability of this is equal to the probability of B minus the probability of A intersection B. So this is equal to the probability of, it's equal to 0.8 minus 0.24, which is equal to 0.56. So those were the four answers. 0.24, 0.3, 0.86, 0.3, and 0.56. Okay, on to the next question. And the next question is, approximately 4% of eggs produced and sold at a local farm are cracked. Jerry buys 24 eggs from the farm. Find the probability that exactly 2 of Jerry's eggs are cracked. Next, find the probability that Jerry buys no more than 4 cracked eggs. Excuse me. Next, find the probability that Jerry buys at least 2 cracked eggs. And finally, find the variance of the number of cracked eggs. Okay, so this is pretty simple. So what we have over here is a binomial distribution where, let's see, the probability that an egg is cracked is a binomially distributed with 24 terms, and the probability that an egg is cracked is 0.04. So first, find the probability that exactly 2 of Jerry's eggs are cracked. That's going to be 24 choose 2 times 0.04 squared times 0.96 to the power of 22, which is equal to 24 choose 2 times 0.04 squared times 0.96 to the power of 22, which I get as 0.118, around 0.180. Okay. And then for the next one, find the probability that Jerry buys no more than 4 cracked eggs. So we can calculate the probability of Jerry buying 0 cracked eggs, 1 cracked egg, 2 cracked eggs, 3 cracked eggs, and 4 cracked eggs, since we'll have to use these later. So this one was 24 choose 2 times 0.02 to the power of 2, 0.04 times 0.96 to the power of 22, which is equal to around 0.180. The probability that he buys one cracked egg is 0.04 times 0.96 to the power of 23, which is equal to 24 times 0.04 times 0.96 to the power of 23. It's equal to around 0.375. The probability that he picks 0 cracked eggs is just 0.96 to the power of 24. It's equal to 0.96 to the power of 24. It's equal to around 0.375 as well. Now 24 choose 3 times 0.04 cubed times 0.96 to the power of only 21 is equal to it's equal to 0.055. And then this is 24 choose 4 of 0.04 to the 4 times 0.96 to the 20 is equal to, sorry, you can't see that. It's equal to 24 choose 4 times 0.04 to the power of 4 times 0.96 to the power of 20. This is equal to around 0.012. So the probability that he buys no more than 4 cracked eggs is if we add up all of this. So we have 0.012 plus 0.055 plus 0.180 plus 0.375 plus 0.375, which I get as 0.997. Okay, find the probability that Jerry buys at least 2 cracked eggs. We just subtract 1 from these two probabilities up here. So it's 1 minus 0.375 times 2, which is 0.25. So it's only a 25% chance that he buys at least 2 cracked eggs. Finally, find the variance of the number of cracked eggs. Remember, in the binomial distribution, variance is equal to NPQ, which is equal to 24. Well, I mean, yeah, I guess it is NPQ. So this is 24 times Q. We didn't go over this earlier. This is 1 minus P. 24 times 0.04 times 0.96, which is equal to 24 times 0.04 times 0.96 is equal to 0.9216. So just under 1 cracked egg of variance. Okay, nice. So next question. And we have for that here. The masses of cans of baked beans are normally distributed with a mean mass of 415 grams and a standard deviation of 12 grams. So first, the probability that a randomly selected can of beans has a mass greater than n is 0.65. Find the value of m. Next, a can of beans is randomly selected. It is known that the mass of the can is more than 420 grams. What is the probability that it weighs more than 422.5 grams? And finally, Ashok buys 144 cans of beans from the supermarket. What is the probability that at least 75 of them have a mass of less than 413.5 grams? Okay, again, tall order, but it's okay. So, probability that a randomly selected can of beans has a mass greater than m is 0.65. Find value of m. So, this is equal to the probability of z being greater than m minus 415 over 12 is equal to 0.65. So m minus 415 over 12 is equal to 0.65, and I get that as around 0.386. So we have m is equal to 0.386 times 12 plus 415. And I got 419.6 as the answer to that. Check that's correct. Oh, sorry, wait. X is greater than m is 0.65. Sorry, so we should be actually subtracting, because x is greater than m is equal to 0.65. So we have actually, this is equal to x is less than m minus 415 over 12 is equal to, or I mean, it's because of the limitations of my probability distribution table. Let's put that back. Okay, here. So as you can see, we calculated it was 419.6, but actually we need to swap these two around. This should be 415 minus m, really, because we know that the probability will be greater than the mean. So what we actually have here, this should be negative 0.386. So we have m is equal to negative 0.386 times 12, and so we have 415 minus this value, so we end up with 410.4 the mass. Okay, next, a cat of beans is randomly selected. The mass is greater than 420. What's the probability that's greater than 422.5? So first we need to find the probability that the mass is greater than, we just have to divide the probability of it being over that by the probability of it being over this. So the probability of this being greater than 5 over 12 over the probability of this being greater than 7.5 over 12. So this is equal to z is greater than 5 over 12. What's 5 over 12? 0.416. Oh, actually, sorry, this should be the other way around. So I'm going to put 5 over 12 at the bottom, and that is 0.416 plus 0.0022. 1 minus this. So I got 0.3387 as that chance, and then 7.5 over 12, 0.625. So we have 0.62. And so I got 0.266 over here. So the probability that's greater is 0.266 over 0.3387, which is equal to 0.785. So there's a 78.5% chance that if it's greater than that value, it will also be greater than the higher value. And then finally, he buys 144 cans of beans. What's the probability that at least 75 of them have a mass of less than 415 grams? So what we're saying is that what's the probability that 75 that's 75 over 144 beans, or no, at least 75. Sorry about that. I just had to use the toilet. Anyways, so where are we? 75 over 144 cans of beans. Okay, we can worry about that later. First, let's find the probability of one can of beans being having a mass of less than 413.5 grams. So that's the probability of Z being less than 415 minus 413.5, which is 1.5 over 12, which is equal to 1.5 over 12 is 0.125. So 125, 0.5478 plus 0.002, 1 minus that. So the probability of this is around 0.450. And so now we have a binomial distribution here. Let's say a variable y, which is the number of cans of baked beans, is a binomially distributed with 144 and 0.450 probability. And we need to find the probability that y will be, what is it? At least 75, greater or equal to 75. And so the thing is, this is quite a large binomial. What would this be equal to? Are we just allowed to use a calculator? I wonder if they would just accept us using a calculator for this and just going like, that's the binomial. This thing. This is a sum of n choose k. Yeah, so what I'm going to do here is, since I do not want to calculate like 100 values of the binomial, what I'm going to do is I'm going to approximate this as a normal distribution. And this is a trick that they didn't teach in the textbook, but it's okay as long as this value is close enough to 0.5 and this value is relatively large. So we can approximate this as a normal. So we can say this is equal to, we're getting 75. So it needs to be greater than 75. And the mean will be half of this. So 144.72 divided by standard deviation of a binomial is NPQ. So that's 144. Oh, sorry, no, wait, the mean isn't 72. This is going to be the mean over the standard deviation, which is NPQ. So the mean is the number of trials times the probability per trial. So this is 64.8 divided by the standard deviation. 144 times 0.450 times 0.550. So this is over 35.64. So we need to get the probability that the standardized function is greater or equal to 10.2 over 35.64. Yeah, so the normal distribution function does not work very well to approximate this function, so ignore that. And instead, at this point, I would just put this binomial and this into a calculator, and we should get the answer of around, I think it's 0.052. So yeah, that was the answer. Okay, and then on to the final question. So the final question is, x is a random variable such that it's modeled by a normal distribution with mean and variance. It is given that the probability of x being less than 110 is equal to 0.10, and the probability of x being greater than 130 is equal to 0.45. Find the mean and the variance and finally find the range of values of x such that the probability of x minus the mean is equal to 0.22, is less than 0.22. Okay. So find mean variance. So we have the probability that x is less than 110 is 0.10. So the probability that the normal function is less than x minus the 110 minus the mean over variance over standard deviation is equal to 0.1, and the probability that this is less than, no, it's greater than 130 minus the mean over the variance is equal to 0.45. So from this we can get that 110 minus the mean over the variance is equal to that should be negative 1.282, and then 130 minus the mean over the variance is equal to where is it? Around 0.12 5478. We need 125. So we have, rewriting this again, 110 minus the mean is equal to negative 1.282 times the standard deviation. 130 minus the mean is equal to 0.125 times the standard deviation. Subtracting the bottom one from the top, subtracting the top one from the bottom one, we get 20 is equal to 0.125 plus 1.282 times the variance, or 1.407, times standard deviation. So 20 over that is equal to the standard deviation of around 14.2. So that should be the standard deviation. And then we need to find the mean. So the mean is simply 0.125 times that. And then we have 130 minus this answer. So we get the mean is equal to around 128. Okay, nice. And then find the range of values of x such that, weird question alert. So the absolute value of x minus, the probability of x minus the mean is less than 0.22. So, okay, range of values of x such that the probability of okay, so assume that x is just evenly distributed. It's a random continuous variable. Okay, and so we need to have half of the values, more or less, half of the values of x are going to be above 0, and half of the values of x are going to be below 0. So of this 1/2, we need to have only 0.22 over 2 of them fall into whatever category, and the rest of them fall outside of the category. So we have 0.5 minus 0.22 over 2 is equal to, and that's equal to the probability that we need to get, which is 0.39. And then so now we need to limit this range. So so that this is equal to 0.39, this is 0.22 over 2. And of course this middle value will be 128. So we have the probability that x will be less than a needs to be equal to 0.39. So therefore a is equal to 0.28, and then I guess we apply the standard we apply the standard deviation. I'm very confused by this question. 14.2. So what? 0.28 is equal to x minus 128. Okay, no. So that's probably it. So if we get this here, then we get x, which is equal to a. Sorry, this should be a over here. Is equal to 124. And then if we do the same for the other side, so the probability that x is greater than b is equal to 0.39 as well. Then that means b is equal to 0.28. It's equal to 128. Sorry, 0.28 is equal to b times 128 over 14.2. So b is equal to 0.28 times 14.2 plus 128. So I got 132 apparently. So this means that the range of values of our variable x must be between a and b. So it's between 124 and 132. So yeah, but that was a very weird question. I don't think it was worded correctly. But that was the final question as well. So that was all for this IB Math speedrun. I hope you enjoyed. And yeah, I hope to see you in the next one. I guess we'll go through the tests, the practice tests in the book, and that was all. Sounds good. See you then.